I have the great pleasure to be with Professor Emeritus Marc Henry, who was teaching chemistry at Strasbourg University, who is author of 10 books, who published 160 articles, and who has been cited at the scientific literature for about 12,000 times, who wrote an, for me, absolutely exceptional article called Thermodynamics of Life. Professor Marc Henry, thank you very much for being with me.
Yes, it was a pleasure for me to...
What motivated you to write this article? And maybe you start, first of all, by introducing yourself a little bit.
Yeah. So first I will apologize for my English, which is not, will be with a French accent, which can be a little bit spicy and which make more fun. So I am not a native American speaking, so I will try to speak in English, but I prefer usually to speak in French. But for this kind of event where, you know, when you are a professor, you should write in English, not in French. So it's a very good thing to be able to speak of this paper in English and not in French, because it will allow me to, it will make me more work, mental work, to make the translation. But I think we will have a much wider audience by speaking English than French. So that's the first point. The second point is when you write this kind of paper, is that you cannot be young. You are supposed to be an old man with a long beard and maybe a little bit boring because we are in science, not in fun or in video and in shows. So it's really a pleasure for me to speak about this paper because, as you told in the introduction, this paper was written for not today people, but for people who maybe will read this paper 2 centuries after it was written. So when you write the paper in this mindfulness, that is to say, I write for now, of course, but I also write for people that I don't know, because it will be the son of the sons of scientists. And this is one of the great advantage of writing and not of talking. That when you write, you give reference, and you cannot say rubbish. All you say needs to be argumented and referenced. This is quite different from speaking. And here it's very interesting because we will speak. That is to say, we will not have the academic point of view with reference, because the references are in the papers. And if you really are interested by what I will saying in this interview, you just have to read the paper and go to the reference. So this will be more a comment on this paper, and it's very rare. It's very rare. Sorry. In science, to be able to write a paper and to comment this paper. Because usually the people who comment the paper are the experts, which says, okay, this can be published. No, this cannot be published. But that the same author writes the paper and makes the comments, it's not very frequent. So I would like to thank you, Klaus, for providing me the opportunity to speak about this paper. And as you understand, after 40 years of research, if you write such kind of paper, that means that you have some things to say. Otherwise, you just shut your mouth. If you have nothing to say, just don't speak. If you write this kind of paper, That is to say, I have things to say, and I think that these things are important. They are not funny or just doesn't write for being cited. I write because I think that biology and medicine are on the wrong way. And they have been on the wrong way, not now, but many years ago. We take wrong directions. And when we take a wrong direction, of course, things cannot be easy. And we all see now in 2022 that medicine is in crisis. We have big crisis in medicine, and the reason for this crisis is not on what we have decided now. It's the decision we have taken several years before that were the wrong decisions. And in science, there is no wrong decision, but there are wrong ways of thinking. What I've called the fossils in the mind. That is to say, science develops with time, and of course, we don't always go straight forward to the good interpretation. We make a lot of errors in science, and then we correct these errors to get finally a final version of science which is clean. But the errors, we have made them, and they are behind us. And if you don't realize that there was errors in thinking, and that you should forget about these wrong ideas to go to the ideas that have been emerged, and what we will speak about of this paper speak about 150 years of not thinking wrong, but of thinking on a complex subject by making errors, and we have corrected these errors maybe 1 century ago. But before these corrections, there was a lot of misunderstandings of basic concept, and this is one of the main reasons I write this paper, because these misunderstandings should be clearly identified, and as there are misunderstandings, you should first identify what was this misunderstanding, and then after, of course, propose new things, the new way of thinking, which is more correct and more in line what we know now here in physics, chemistry, and biology in 2022. So, what I would say that when we look at medicine and biology nowadays, 2022, is that we are in the 20th, that's my problem with English, 21e siècle.
21st.
20th, yes,
20th century, 21st century.
20th
First
century. This is our body, but our mind are in the 19th century. That's a big problem, because we have a body which lives nowadays in a complex world with a lot of chemistry, a lot of problems, but our mind are still, for most of the physicians and the scientists, the mind is still in the 19th century. So this should be corrected. That is to say, the first thing to do is to put our mind in phase, in line with what we know in 2022. And what is the knowledge, the scientific knowledge in 2022? It's basically two things. When you speak about, I would say, the atomic world, atoms, molecules, we should use quantum physics. This is the right way of speaking about nature. When we speak about galaxies, black holes, stars, we should be with general relativity. These are the two main way of thinking that we have to use if we want to be correct now. But then we have a trouble, because when you say atoms and molecules, okay, that they're infinitely small. When you say galaxies, black holes, this is infinitely large. But we are not infinitely small, we are not infinitely large. So our trouble nowadays is what language I should use. Me, the man, a human being, I am not at the size of an atom, I am not the size of a galaxy. So I am the size, typically 1 or 2 meters height, maybe 100 kilograms of mass. When I live, what matters is seconds. What science I should use? General relativity or quantum physics? When I ask these questions, I have a definitive answer. I should use quantum physics. This was the answer I understand from knowledge of what science has evolved. And then I ask myself, okay, that's quantum physics. But what is the concept which is common to quantum physics and general relativity? What is the concept which is the same, which we should use when you are at the atomic level or at the galaxy level? And there was just one answer, entropy. Entropy was the reason why we have to go to quantum physics. Because one of the big problems at the beginning of the 20th century, what had been called the black hole problem. No, not the black hole, the black body spectrum. The problem was very easy to understand. You just take an oven. And an oven is characterized when you want to cook your chicken. The first thing you have to think, what temperature? If I go too high, the chicken will be burned. If it is too low, the chicken will not be cooked. So you have to choose the right temperature. But what we all know from ovens is that if you select, for instance, 280 degrees, which is fine for cooking a chicken, the oven will not emit X-rays or gamma rays. It will just keep at this temperature. You will have infrared for cooking the meat, but not X-rays or gamma rays. And at the beginning of the 20th century, the problem that's the theory, the way we are thinking about the nature. We have, in fact, two kinds of equation, which we call the Maxwell's equation for light and the Newton's equation for matter. And when we apply these two fundamental equations to the problem of the oven, which is at a given temperature, the prediction that an oven should emit X-rays or gamma rays. And we never see that. Mm-hmm. So we have a theory. You say you just put your button on 280 degrees and you get X-rays and gamma rays. This is a theory, the theoretical consequence of your equation. So what is the trouble? We don't observe that. So you have two ways of resolving the problem. The first way is to say, wow, there is something wrong with my button. The button is not working, so I am emitting X-rays. But as you all know, the button is not the problem. The button is okay. The other trouble could be that the theory is wrong. It's not the oven which is the theory. And this was the way that had been investigated by scientists. They say, okay, the theory is wrong. So what we should do? And the only answer was, what is an oven? It emits infrared in form of heat. And what is the concept in the 19th century which is related to heat? It is not energy, it's entropy. That is to say, at the very basis of the birth of quantum mechanics and quantum physics, we have the problem of entropy. We have entropy, and entropy says that we should go this way, and the experiment shows that we are not going the way. So that means that there is something wrong, and we have to rethink. And this was a very, it takes about 30 years to solve this problem of the black body spectrum. In fact, it was solved very early by Max Planck. He get very quickly an equations. But, you know, Max Planck, when he write down his equation in, publish his equation in 1901, sorry.
1901, yeah.
1901? He was honest, because he said, this is a good equation, of course, because we have the experiment, we have the equation, and this fits nicely. But he has the honesty to say that this is a good equation, but I don't know why. I know, by intuition, by feeling, or by just seeing that is the right equation. But I cannot understand why it should be like this, because he was introducing a new concept in physics, that the energy, which is emitted when you heat a body, it emits energy, and this energy is not emitted in a continuous way. It is emitted by quanta. That is to say, you may emit one, today we call this quanta of light are called photons. You could emit one photon, you could emit 2 photons, you could emit 3 photons, but not 1 photon and a half. This makes nonsense. You need 1 or 0, 2 or 1, 3 or 2, but not 2.5 or 2.3. And this was a revolution in physics, because this gave what we call quantum physics, because quantum in Latin means how many. When you want to say how many, in Latin you say quantum. And when you say how many apples, you don't say 2 apples and a half, or 10 apples and 1/3. You say 10 or 9 or 11. That is to say, you use integers and not real numbers. And this was a deep revolution in physics to understand that we have to speak with integers and not with real numbers. And so that was the starting point. And what is interesting for the paper we are talking about is that at the very beginning it's related to entropy, in fact. Max Planck was a genius of entropy. Maybe Max Planck will be the only man in the 20th century which just understand what is entropy. Because entropy was introduced by another, not by Max Planck, but by Ludwig Boltzmann. Ludwig Boltzmann told that there was a thing called entropy, and his problem was to understand the supposition of the hypothesis of another scientist, which was Rudolf Clausius, which are putting in equations the fact that when you have a thermal engine and you fuel it with energy, you cannot recover 100% of mechanical energy. You have always a loss. This was the work of Clausius. In fact, this was not the word of Clausius, it was the work of a French guy, which was Carnot. Sadi Carnot was the first to point to this effect. To say you put energy in an engine, and what you recover is not 100% mechanical energy, but maybe 8% and 20% heat. So this part of the energy which is transformed into heat was called entropy, in fact, with the temperature, just the temperature which is a scaling factor for this entropy. And Boltzmann was, Clausius, Carnot was saying that we cannot have a 100% engines, it's possible. And Clausius was at the mindfulness of saying, okay, why we cannot get 100% mechanical energy? Because there is a thing called entropy that you should produce, and when you produce entropy, you cannot have mechanical energy. And the idea of Boltzmann, because Clausius says that he enunciated two principles for what we call thermodynamics. Now, that the sum of all the energy in the universe is constant. This is what is called the first principle of thermodynamics. And the second principle of Clausius was that once you get a situation, the universe will always evolve in order to maximize entropy. That is to say, if you have several ways of evolutions, nature will always select the way which gets the maximum of entropy at the end. And this was the problem with Boltzmann, that he was trying to understand why we have to maximize entropy during an evolution. And he performed a very beautiful job. He put a little formula, which is in the paper, which is Boltzmann equations, which relates entropy to all the microscopic representation of your system that you can have. That is to say, when you say I am at 20 degrees and 20 Celsius of temperature, if you try to understand this, what means 20 Celsius in terms of energy, it means that you have molecules which are going very slow, molecules which are going very fast, but if you take an average between those we are very slow and those we are very fast, you get this average energy which corresponds to 20 Celsius. And so we have this understanding that behind temperature there is a way of characterizing the speed of the molecule, but not the individual speed, but the average speed of a big number of molecules. But the key point is that you have, of course, the average speed, but you have also molecules which go slower and molecules which are going higher. And there is a deep link between this way of thinking of about speed, because before thermodynamics there were mechanics. And in mechanics, the main problem was not the speed, it was the position. You have an object which moves with time, and the problem with people who are making mechanics was can I predict what will be the positions of my body after a certain amount of time? And here we all know that we learn this in high schools, that we have the Newton's equation, which allows us to calculate what will be the next positions if we know position at a given time. And so Boltzmann realized that we have in fact a problem with two basic entities for one particle, if we just limit to one particle. What is its position? Where this particle is at a given time? That's the first information we need to make physics. But this is not enough. Because at a given time, at a given position, we can be at 0 speed, or we can be moving. So we have also to specify the speed. And here he became to realize that there was a quantity, which is called entropy, which measure on how many positions we can be, or how can be our different speeds at a given temperature. That is to say, if I say 20 degrees, that means that I can be there, but not there. Because my average kinetic energy is not enough to go there. So I stay here. And then after, of course, you have to localize the particles in the space, where it is, but also where it is in the speed. That is to say, as my speed is small or high. And again, the temperature limit you. You can be slow or high, but if you want to be very fast, you will be very few molecules. That is to say, you have also a dispersion in space. What we call the dispersion in space is called the volume. And we have a dispersion in speed. That is to say, in this volume, we can go at a slow speed or at a much quicker speed. And entropy measures what is allowed at this temperature, where I can go in space and when I can go in speed. And this is a very powerful definition of entropy. But strangely enough, it's not the definition which is used by scientists. If they use this definition, there will be no trouble. And I will not need to write this paper. Because this is what is entropy, is really where I am in space and where I am in speed. In fact, it's not really in speed, it's in the amount of movement. It is a product of mass by speed. But as usually the mass doesn't change during a movement, we can speak about speed and not about amount of movement. But technically speaking, it's amount. You should take into account the mass. And this is important when you go at velocities which are close to the speed of light, because from the special relativity of Albert Einstein, we know that the mass changes with speed. So, to be honest, we should take the product of mass by speed, not speed alone. But as we are speaking for people who are not, which may be not very acquainted with physics, I just say speed. But it should be understood that it's a product of mass by speed, which is what measures entropy. And this was the right way in thinking, and there is a mathematical formula which is given in the paper, which that every scientist should use. It is the famous Boltzmann equations, the basis of statistical physics. But strangely enough, it is not this equation which is used. When you go to a scientist and you say, "Oh, guy, what is entropy for you?" Say, "Oh, it's disorder." He will tell you that, well, what we see in nature, that is order. When you see a tree, there is an order because you have the trunk, you have the branches, you have the leaves, and you will have no idea to mix the trunk with the leaves. You have what we call a structure. And when we have a structure, we speak the language of entropy, we say, oh, the tree is a system of low entropy. Low entropy means that you can have structures. But what happens if you go to high entropy, then you lose the structure. And here comes, I would say, a bifurcation in thinking. That is to say, by thinking we lose structure, you are keeping correct with the Boltzmann definitions. Because a structure, when you say a structure, that means that the movement of the small particles which are constituent of the structure should be low enough in order that the particles keep the same positions. This is definition of structure. We have movement, but this movement has not enough kinetic energy to change the positions. If we increase the temperature, of course, we get more energy and the position will be changed, and we say we have lost the structure. And Boltzmann say, okay, we have lost the structure because we have increased the entropy. Because as soon as you can go, the particles can explore a more larger volume, that means that they have a larger entropy. And entropy is an additive concept. It is to say you add. If you have a certain number of particles, you just add the entropy to get the sum of all the entropies. And of course, the larger the volumes can be explored by one particle, the larger will be the entropy. So here when you say, I increase the entropy, I lose structure, it was still okay. It was still in the right track. But now there are people that say, oh, we are losing order. That's another thing. We are losing order. Or, if you prefer, we are going to disorder. We put into the thinking, the way of thinking, a concept which is order or disorder, which has nothing to do with what is entropy. Entropy is not a problem of order or disorder, it's a problem where I can move in space, where I can move in speed. How much speed I am allowed to have. It's not a problem of order or disorder. And it was at the very beginning of the 20th century that some scientists, to explain what is entropy, they say, oh, you layman, you are idiot, stupid. You are not able to understand what is entropy because it is a statistical concept. You have the concept of position, of spin, and you are too idiots for understanding this. So as you are too idiot, I will use something I could understand, which is disorder. That is to say, I will say that when there is structure, there is order. When we have no structure, there is disorder. And this was the beginning of the end. Because the beginning of all troubles nowadays, that is to say, we get a wrong interpretation of what is entropy. Instead of sticking to the Boltzmann definitions in terms of position and speed, we go to this concept of disorder, which is a subjective concept. I will just give you an example. You always, we have books here. It was an idea of Dan, which is the man which is recording. Thank you, Dan.
Hello. I'm behind it.
You play a job in this kind of interview, so I thank you. So this is Dan. There is always somebody which is behind the videos, and he should be acknowledged. And Dan told me all the books are okay. It's okay for the shooting. And he told me also, I say, maybe I can make order. That is to say, you see, you have some books which are well aligned, and there is some books that are not. Why? Because I am reading the books. And when I read the books, I need to put it out and to put. So there is disorder, in fact. I put disorder. But I can tell you that this disorder is very important for me. Because if I line up the books, I will not be able to find the books I am searching for. But if the books are disordered, that is to say, I can tell you immediately where is the books I want to show you. So you see, the concept of disorder is subjective. That is, what is my disorder is not your disorder. And this is a key point, that is, disorder has no units. When you speak about disorder, give me an unit. It's in amperes, volts, meter, seconds, joule, Weber. I need to say that in science we have a whole range of units, and there is no units for disorder, because disorder in your mind is not in the matter. The matter is not disordered. The matter has mass and speed. Doesn't have disorder. What is disordered? You can have disorder in the mind, but this is called schizophrenia. And the matter has not mind. So saying that entropy measures the disorder is just crazy. And of course, entropy as a unit I can give you, it's joule per Kelvin. Joule is the unit of energy, Kelvin is the unit of temperature. So as the entropy as a unit and disorder has no units, you cannot identify entropy and disorder. And this was the whole reason for writing this paper. It was the starting point. I must explain to most of the peoples, whether they are scientists and whether they are not scientists, what is entropy. And if I need several pages, because entropy is not disorder. Otherwise, what I would just need, doesn't need to write this paper. I would just, entropy is disorder, and it would be finished. If I need several pages, is that because entropy is not disorder, and if entropy is not disorder, what it is? And here, I have explained you, it is my ability to explore space and my ability to have a certain distribution of speed. This is not disorder. And I have to write this down to be clear. And then after, of course, when you are on the wrong track, you say entropy is disorder, you soon get into troubles. Because if entropy was a side-by concept, that is to say something which is just, okay, it's interesting for specialists, but we can do without entropy. Of course, being on the wrong track will have very teeny consequences. But when you realize that entropy is not on the side, it is on the art of medicine and biology, if you are on the wrong track, that means that the whole biology thinking and medicine is on the wrong track. And now you are terrified because medicine is healing people which are ill. And if we are on the wrong track, we cannot heal them. And now you have a responsibility. Because you know that entropy is not disorder. And you know that thinking that entropy is disorder will put medicine and biology on the wrong track. So that we won't heal people. And even if you don't, the best will be not to heal them and just to say, well, okay, you just keep them in their present state, but that's not what happens. That is, say, not only you don't heal them, but you get them sick because you are on the wrong track. And now you have a responsibility because you cannot just say, this is not important. Because life depends on what you are writing. And life now, and life in several centuries after. Because if we don't change the way we think about entropy, our children and small children and children of the children of the children, we have the same problem as us. We need to go again on the right track. And that was one of the main motivations for writing this paper. Sorry to have been so long. But in the final state, we we have a physical concept which has a misunderstanding at the basis, and here we pay by lives this misunderstanding, life and death. So when you have this knowledge, you need to write this down. And this was the very motivation for this paper. I call it Thermodynamics of Life, because it is devoted to what is life, and not from Schrödinger's point of view. It is demolished in the very first lines that Schrödinger's make a lot of harm to biology. So what is life? And thermodynamics. Why? Because the science of thermodynamics, the birth was the first birth was when we identified the concept of energy, and the second birth when we identified the concept of entropy. And of course, when you have two concepts, you have a trouble. What is the most important, energy or entropy? Because we have the two. The first principle, which says that energy never changes, it's always the same. What you only can do is to change energy, so you have kinetic energy, thermal energy, you have potential energy, you have electrical energy, you have mechanical energy, you have nuclear energy, you have any kind of energy you want. And that's the trouble, that energy is what you want. But the second one, entropy, is single. There is not mechanical entropy, there is no electrical entropy, there is not nuclear entropy. There is just one thing, entropy. So if you have to choose between these two concepts, energy, which is what you want, and entropy, which cannot be what you want, which is just a single thing, of course, the important concept is entropy. Because it has just one definition, and it can be applied in any kind of situation with the second principle. To say entropy should never decrease, but you should add this sentence, these words, that if you forget these words, everything goes down. Entropy should always increase, but which kind of entropy? The entropy of the whole universe. Not a teeny part of the universe. The whole universe, taken as a whole, should always increase in entropy. And the drama, and this was mainly for the fault of Schrödinger's, but to say, no, a small amount, a small volume of space should increase its entropy. No, the whole universe. That is to say, the real message of entropy is that it connects what is happening here on Earth to what is happening on the whole universe. And when I say the whole universe, it includes what happens in black holes, at the frontiers of the universe. That is to say, we are living in the universe, we are not living on Earth. Because Earth is just a small part of the universe. We are people of the universe. That is to say, a thing which has, here I have a problem with English, 14,000, billions light years of size. And this was the point of view of a physician, which we call Ernst Mach. He told this. That is to say, what happens on one point in the universe depends on the disposition of the whole matter in the whole universe, not on only the local configurations. And so entropy makes us a citizen of the universe. And I think that is a very beautiful idea, that we live in the universe, not on